Hi guys, in this video I'm going to go over some code to demonstrate the generalization and bias variance trade-off. I'm not going to run this code, I'm just going to go over it and show you the results. So first we are going to import some libraries, Torch for neural networks, NumPy for just general array stuff, matplotlib for plotting, and sklearn. We are going to use the train test split to split our data into a training and validation set. This is just for plotting that it looks better and bigger. And this is for reproducibility. I'm going to set a manual seed so if you guys run it, you will get the same results. So I'm going to use a polynomial regression. So our y will be equal to this mean function, which is a polynomial regression, plus some noise. In this case, it will be equal to a normal random distribution with standard deviation of 0.75. And if we take x to be 10 points equidistant between -3 and 3, and this is our mu function, the true mean, we add some noise to it, and then we plot it. It looks like this. These are the points. And what we are going to do now is we are not going to use neural networks. We are just going to use linear regression. So why linear regression? Because, well, if we expand x, the regular x, and we also take x squared and x cubed, etc., then the model will still be linear with regards to the coefficient. So we could still use linear regression on this expanded x, on this x, which is projected to a higher dimension, you could say. And so at this point, we can use the normal equation, which is simpler and faster for us. We could also use the neural networks, to just take much, much longer to train and everything. So this is what we're going to do. We're going to fit this linear regression for a set of degrees. So either a polynomial of 0 degree, meaning just a constant, 1 degree meaning a straight line, 2 degree meaning a quadratic, 3 meaning a cubic, and 6 degree polynomial, a 9 degree polynomial. Okay, so for each of these degrees, we are going to create this expanded x, or this projected x. Then we are going to just use the normal equation to get the coefficients. Then we are just going to plot the result. Okay, we are going to create this x test with a lot of points, expand it to the new dimension, use the coefficients that we found, and find the y test. And then we are going to plot this. And eventually, we're also going to plot the true points. And if we do this, we get these curves. We can see that for degree 0, we are just getting a constant. For degree 1, the orange, we are getting a straight line. For degree 2, it doesn't really look like this. It's not a straight line, it's a quadratic, but we don't really see much of it because the plot is too narrow. Degree 3, the red, gives us a cubic, and it looks pretty good, not surprisingly, because the data was actually generated from a cubic. Now, what we are going to do is to calculate the generalization error, the mean squared error, but not just for a single point, but for the whole set of points between -3 and 3. This is called the integrated mean squared error, because we are taking the mean squared error and we are adding it up over the entire line segment that we are doing this. And so in order to do this, we need access to the mu, but this we have because I've generated the mu myself, so I know what mu is, yeah? But we also need access to the mean of f and to the variance of f. We don't have access directly to this, but we can create a Monte Carlo estimate, basically run it for a long time, create a lot of simulations, and then take the mean and the variance of the different f's that we will get. So we will do this for 1,000 times. We'll create new data and fit a new model 1,000 times every time. We will do it for polynomials of degree 0 till 9. We will use 100 points between -3 and 3. This will be the integration. So we will take the points, we will sum the error across 100 points between -3 and 3. So, and this is just some things we need. So these are the points, and this is the means. This is the true value for these points. So now we are going to store the different f values, the different model values for each degree, and then for each run of MC. So for each degree, we'll create our X matrix and our X test matrix. So for each MC iteration, we will sample new data, and then we will train. In this case, it's just using the normal equations on the data. Then we will predict for the entire line between -3 and 3, and we will store the values. Okay, and now we can actually compute the bias and the variance the bias, we will take the mean over the different MC runs, subtract from it the true value, square it, and then we will add it up over the entire line, right? Because we do it for each point, but we add it up, and then we will get some bias for each degree polynomial. So we will have, in the end, this will be a vector of the squared bias for each degree of polynomial from 0 till 9. And for the variance, we'll do something similar. We'll just take the f values and we'll take the variance of each value across the different MC iterations. And then also we will sum it up across the different points between -3 and 3. And then we can also plot it. And if we'll plot it, we'll see this thing over here. So the bias squared, it's the blue thing. We see that it starts relatively high, then it drops really low for 3, and then it stays more or less the same, maybe adds a little bit here, but it's almost unnoticeable. The variance, it's the orange term, it starts very low, but then after 3, it starts to grow and grow and grow. And so the integrated MSE, the generalization error, is just the sum of these two. We see that it starts high, goes down, and then goes high again. So the best point will be a polynomial of degree 3, which is again not surprising because this is the actual polynomial degree of the true process. Now we can also do this for neural networks. I'm not going to do this. I'm just going to recreate this graph over here, but I'm not going to calculate the IMSE. It will be too much work to train the neural networks again and again. So I will just create this class polynomial regression neural network. It will have one layer. It will be a linear layer projecting from whatever degree that I give it to 1. We are not going to use a bias. We are going to give it explicitly. And then the forward pass is just passing the inputs through this linear layer. Okay. And we are going to use the mean squared error as the loss. Note that this is not the same as the mean squared error of the generalization. Okay, this mean squared error is just the loss for a single data set, and the generalization MSE is the loss over all different possible data sets. Okay, we will also use the Adam optimizer, and we will train for these polynomial degrees. So for each one of them, we will set the seed. We will increase the degree by 1 just so for the range here will be acceptable. So a degree of 0 means that we want x to the power of 0, and that's it. But a degree of 1 means that we want x to the power of 0 and x to the power of 1. So this is why we are increasing here by 1. We are instantiating the neural network. We are creating the loss and the optimizer. And then we are training for this amount of epochs. And here an epoch is just 10 points. Yeah. So we are passing through the 10 points really quickly. We are doing a forward pass, calculating the loss, which is the MSE, then doing backpropagation. And finally, for each degree, we are plotting the results like before. And this is the results we are getting now, very similar to the results from before. So you can take now this and maybe do this and try to do the IMSE. It will be very, very long because you will have to train this network again and again 1,000 times, or you can do less or more, and then average all the results. But you will get something very, very similar to this. So the bias should decrease as you increase the complexity of the network and basically add more polynomial degrees. The variance should increase, and the overall IMSE should be the best for 3. Okay, but as mentioned, in real-world problems, we can't do what we just did. We can't plot the results and say, oh, you know, the red line looks like it's the best. The blue, green, and orange seems too simple, and the purple and brown seems too complicated. No, and we also don't have access to the true mean, so we can't calculate this. So what do? We divide the data into training and validation sets. Okay, so we did this here. And so in orange are the points that were chosen to be in the validation set, and in the blue are all the other points. Now we can train a neural network, and we keep track of both the training loss and the validation loss. And here I will start to keep track only after 100 epochs, because again, in the beginning, the neural network is so messed up and we have so little data, just 8 training points at this stage. So I want to give it some times, and so that it doesn't just give random results in the beginning. So I will start tracking that from the 100 iteration. And I'm doing exactly the same. I'm projecting x into a polynomial matrix. I'm doing the same for xval. I'm creating a model, the same loss function, the same optimizer. I'm telling it that I'm in training mode here, so keep track of the gradients. I'm doing a forward pass, calculating the loss function, doing a backprop. And then if I've already passed 100 iteration, then I'm starting to keep track of the training loss. Then I'm telling it, okay, move to validation or test mode. Don't keep track of the gradients. Do a forward pass on the validation set, calculate the loss for that, and keep track of that loss as well. And then I want to also keep for each epoch the final model that was chosen. So I'm going to take points from -3 to 3, expand them, pass them through the model, through the final model of each degree, and keep that result because I'm going to plot it later. And now I can print the training loss and the validation loss of the last epoch of each degree polynomial. And we see that we get something like this. So again, the best result seems to be around 3, and it gets worse after that because the training loss maybe doesn't get worse, but the validation loss gets worse. So we should choose degree 3. And what we can also do now is for each degree polynomial, plot the training loss and validation loss as a function of the time or the training periods. Okay, so here is for the 9-degree polynomial, we see that we have some training loss. It goes down and down and down. And the validation loss, at first it goes down, but then it starts to go up. Right about 500, it starts to cross and gets worse than the training loss. And it just gets worse and worse from there. And so this is an indication that we are suffering from overfitting here. Now, if we do the same for a polynomial of degree 3, this is the graph that we will get. And you see that the training loss goes down and down. The validation loss also goes down, and it doesn't go up. So we are actually, it's really close to one another. So this looks like a perfect model. And it's not surprisingly, again, because the true model is actually with a p = 3. So no surprise here. But this model seems to have low variance and low bias. So no overfitting and no underfitting. Finally, let's compare with a polynomial of degree 1. So basically a straight line. And if we plot the train and validation loss, we see that actually this model has high variance because the validation loss is much higher than the training loss. And it's changed position somewhere around here, maybe 100. This is 100 epoch. It starts at 100 epoch, so maybe 150, it starts to really get worse. But it also has a high bias because look, this doesn't get better. Here it went down to almost 0. Here it stays at around 20. So this model seems to both be underfitting and overfitting. It has high bias and high variance at the same time. If we plot it, it looks something like this. It has a high bias. It's pretty obvious. It doesn't fit the true lines, but it also has a high variance because it only fits to the blue points and not the orange points. And it could be that if it had the orange points, maybe the line would shift a bit and yeah, the validation loss would be less. And here it's a mistake. It should be degree 1, not degree 9. Okay, so this is all for this video. I hope it gave you some more intuition and understanding about the generalization and the bias variance trade-off. I hope you enjoyed and see you in the next one.